All right, so welcome everybody to already lecture number 4 of the series on functional programming. And today, finally, we're going to get down and dirty and really kind of write some code. Last week we talked about types, which is a nice topic, but you know, nothing is as exciting as writing code and defining functions. And that's, of course, what functional programming is all about. Programming using functions. So let's get started right away and look at how in Haskell you define functions. And what I will do along the way is, you know, abstract from the specific, wow, what a word, I have to get started here. To abstract from the Haskell syntax and see, you know, how these things will look like in other languages. So let's define a simple function. So this is the function that takes an integer to an integer and takes the absolute value. Again, you know, we're not trying to define any meaningful function, it's just to illustrate the syntax. So in Haskell we write this as follows. So you define first the type, as we have seen last time, abs double colon int arrow int. And then we define the function straightforwardly as you expected with a conditional. So if n is greater than or equal to 0, then it's n, and otherwise it's the complement of n. And of course, you know, you don't write, you know, the kind of greater equals like this, but you use the ASCII representation. But for the rest, this is kind of, you know, as close to concrete Haskell as you can get. And again, you know, this doesn't look kind of that different from say C#, except that it's one thing that I want to emphasize, that in Haskell, you know, we separate the type specification. So the type, which is like int arrow int, from the function definition itself, you know, abs of n equals that big expression. Whereas if we would look, and I'm trying to use a different color here, if we would write the same function in C#, you know, or let's use VB for today. You know, in VB we would write function abs n as int as int. So in VB or C#, you kind of intermingle the function definition and the type definition. So, you know, there's the type and the function are kind of intermingled. Interesting thing about VB syntax, which I personally quite like, is that in VB you put the return type, you know, here as an s, whereas in C# you would put the return type in the beginning of the function. So in some sense, the VB syntax is much closer to the kind of, you know, mathematical syntax here that we use in Haskell, where the arguments kind of, you know, the types of the arguments are given first, and then you end with the type of the function itself. And of course, like any other construct, you know, you can always compose things. So like in this function that gives you the sign of a number, right, where there's a nested conditional. So it says if the number is less than 0, then the result is -1. If the result is 0, then it's 0, else it's 1. In Haskell there's not the kind of classical if then else if construct. It's just you put another conditional inside the else part. And then what, you know, we refer to here in the ambiguity with nested conditionals, that's an interesting kind of research exercise for homework, is you look for the dangling else problem. So this is a problem, a syntactic ambiguity that languages like Pascal have, where if the else part is optional, you can get into syntactic ambiguities. And most, you know, I think maybe C also has that same problem. But again, that's just a parsing issue. All right. Now back to lecture 1, where we said in Haskell we put a lot of effort in making our code look as concise and as beautiful as possible, and to make it look as close to mathematics as possible. So another way to write function definitions is, instead of using conditionals, you use what we call guarded equations. So let's write an example using guarded equations. And this is what you often do, when you speak about functions, or in fact a lot of math textbooks use that. So, the absolute value of a number is, well, if the number is greater than or equal to 0, then it's n, and otherwise it is minus n. Okay, so now what we've done is we have moved the conditional from, from the right side of the equal sign to the left side. So we have now kind of, a set of here, oh, there you see my schedule. We have turned this into a set of guarded equations. So these are called guards. And they are called guards. Why? Because they guard the right-hand side. So, if this condition is true, then the value is that. If this condition is true, then the value is that. And there's, if you look at older functional languages, and I think at some point Hugs even supported this, and that's a syntax that I actually prefer. You could write it like this, and Miranda did that. So if you write the absolute value of n equals n, and then you can write here comma, n greater than 0, or it's minus n otherwise. And this is a similar form of a guarded equation, where you push the kind of guard all the way to the right, and this is actually the notation that I prefer. And I think Perl and maybe Ruby have a similar thing, where you can put the kind of condition after the branch. It's like something when some condition. So that's kind of you can read this thing as like when. And so that's kind of another notation that I personally like, and that you see appearing in other languages as well. All right. So why are these guarded equations useful? Well, it's often when you have multiple cases. So that the other example that we saw that used these nested conditionals, it's much easier to write it using this guarded equation notation. And I'll use the when notation here. So if we want to have the sign of a number n, well, what do we say? Well, if the number is negative, we say that the sign is minus 1. If the number is 0, then the sign is 0, and the sign is 1 otherwise. So this is kind of how I would write this equation, and then in Haskell you will see that you just put these guards here on the left of the equal sign with a vertical bar here. But again, it's all kind of a way to structure your definitions, where you want to kind of separate what is important and what is less important. So you want to see the conditions like in one glance, and you want to see the values in one glance. And with a normal conditional, it's much more, again, intermingled. You want to kind of separate that. So here you see the same principle that we apply for types. Instead of intermingling the types and the function declaration, we split them apart such that you can kind of look at them independently. And the same here, when you define a function by cases, you kind of separate very clearly the condition, either by kind of putting it here on the right side or on the left side, no matter how you stand there, and then the actual value. So you kind of clearly separate the two. Then I use here otherwise. Well, otherwise is nothing more than just defined as otherwise equals true. So that's just a definition for true that reads a little bit nicer. One more thing here is that, so in Haskell you use double equals for equality, and then single equals here for a definition, and that's kind of consistent with C# or other languages where you use equals for assignment. Well, in this case it's not assignment, but it's kind of declaration, and double equals for equality. And that's so that's kind of a little bit non-mathematical looking, and if you look into VB, that they maybe have solved that a little bit nicer. But there's some kind of a little bit of syntactic noise that you need to do, otherwise things would become way too ambiguous. Like in this, we'll see an example later, I will point that out. All right, so now when you write these functions here using cases, that's actually not the most common way to define functions in Haskell. So let's kind of look at what we do instead. So some people even say that like pattern matching is one of the big features of functional programming. And it's true, while it's true that a lot of functional languages have pattern matching, really what pattern matching is, it's the analog of dynamic dispatch in object-oriented languages. So let's look at the kind of example here where we define not. So that's a simple function on Booleans. So the type of not, well, it's a function that takes a bool and returns a bool. Okay, and then, well, how are we going to define that? The way we do that in Haskell is since we know that Booleans have two values, true and false, we just write out all the possible cases. So we just write, well, since we have to define a function on the Booleans, we have to define what its meaning is for true, and we have to define what its meaning is for false. Well, negating false becomes true, and negating true becomes false. So here I've defined a very simple function using case analysis on the possible values. Now, I said, this corresponds to dynamic dispatch in an object-oriented language, because in an object-oriented language like C#, and again, I'll stop mentioning C#, I'll just use, C# as my example, but it applies to any other functional language. How you can encode the same program, and don't kind of pick on me because for this simple example that doesn't make sense. But I'm trying to explain like a general mechanism here. What you would do when you have a type like this, you define that as follows. I have a class bool, which is an abstract class, and let's put a method in here, and let's say that's virtual. I won't write that down. And then, so that corresponds to the type bool, and then for each possible value I will define a subtype. So now I bend on my knees for the great Boolean type. So we define class true, which inherits from bool. And now we define, we have to override not. And since this was true, we return new false. And similarly, I don't know if you can get this low grade. So when we have the false type, which is a Boolean, and now I have to define bool not, and I say return new true. Okay, So now we have these types side by side, and now you can see that really they convey the same information. So there's not, that's here defined on false. Well, there's here not defined on false, because here implicit is the this parameter, which in this case has type false, and if the this parameter is false, I return true. So in this case, if I call this thing with false, I return true. So here you see that information that's in here, and similarly, when I have a value of type true, the receiver has type true, then when I negate it, I return false. So the kind of important information is this, and you see that kind of appearing here. So I don't think that as an object-oriented programmer, you really have to have envy of pattern matching, because pattern matching is really, you know, what you would do in a traditional object-oriented language using dynamic dispatch. We'll see more examples later where you can pattern match on multiple parameters. That would kind of correspond in an object-oriented language to multiple dispatch, where which is like kind of harder to define, because usually you only do dispatch on one type, on the receiver. But in practice, really, you know, even in Haskell, people kind of write their definitions that they do only pattern matching on one argument, and then internally they do pattern matching on other arguments. So if you ask me, I actually prefer dynamic dispatch over definitions by pattern matching. And you know, there's enough room here for improvement to improve the syntax of the object-oriented language. But again, you know, it's a little bit noisier, but not that much noisier. But again, lesson here is pattern matching is just another way of doing dynamic dispatch. Also, a downside of pattern matching is that you're kind of really exposing the kind of structure of your types. Whereas with dynamic dispatch, you know, you can kind of hide that a little bit better. If you look at F-sharp's pattern matching, they kind of go around that, and Scala has the same, where you have like special functions that kind of deconstruct a value that you can then pattern match over. But the Haskell style pattern matching in some sense really makes all the fields or all the properties of a type public, because you can kind of match over them. So Haskell in that sense is not very good in modeling, because you have to make, it's like making all your fields or properties public on a class, which is not what you always want to. All right, so here's as I said, sometimes you want to do a double dispatch, and here you see in this example where we're defining and. So I'll write, you know, one case of that on the board here. And is a function that takes a bool and returns a function that takes a bool and returns a bool. So remember from last time that function arrows associate to the right. So when I write this function, it's not a binary function, it's a curried function. It takes a boolean and it returns a function that takes another boolean and returns a bool. And now when I define that, I say, you know, when it's true and true, well, that's true, etc. Now here you see that I'm putting the double AND in parentheses. And that is because this thing is defined as an infix operator. And whenever you have an infix operator and you put parens around it, you can use it as a function. So that's kind of a little trick that we will see later, which is called sectioning. So in Haskell, you can take any like operator like plus, put parens around it, and then you get automatically a function. So you don't have to write a lambda expression. However, if you look at this function here, really, you know, the definition by pattern matching doesn't really reflect the fact that it's a curried function, right? Because really, if you look at this function, you want to think about it as something that takes a bool and returns a function that takes a bool to bool. So if you're really pure, and I'm a real purist, the way I would do it is I would say, I would define it like this. Given true and x, then now I would kind of say, okay, because I do pattern matching on this argument, and then I just leave this one as x, and then here I would say, that is true if x equals true, and it's false if x equals false. Right? And then I would say, if the first argument is false and the second argument is x, so I would kind of define it like this, where I would kind of also split the pattern matching into multiple parts. And here, you might even rewrite this to use pattern matching here as well. And then in some sense it becomes exactly how people encode a double dispatch in object-oriented programming. So as homework, what I will give you for homework is to define AND like this in your Boolean class using a double dispatch. So it's like the visitor pattern. That's what you will have to write. So it's like, I will write them down here. Define AND on class bool using double dispatch. And I think what you will see is that it's not that bad. And again, it's not very common. It's not very common that you're doing pattern matching on many parameters at the same time. All right, but again, Haskell is all about conciseness. So if you look at the definition of true, really it's only true when both the arguments are true, right? So, true and true, well, in that case the result is true. But in all other cases, it doesn't really matter what the arguments are, it's always false. So in Haskell you can do this, what is called a wildcard. So this is like a pattern that matches everything. Now the funny thing is that many people don't realize is that in C# underscore is also a valid identifier. So I often, when I kind of don't care about the name of a parameter, you just wipe this out. So what I actually often do when I define a generic method in C#, for example f, or let's do a generic type, that's more fun. So when I define a generic type in C#, say class, list, and then you usually say list of t, but I don't know, I don't like to invent names. It's always like, what is t and whatever. So if I have a type with one type parameter, I usually, or often, just call that underscore. And now that looks quite beautiful, because now I have a type list of, and it looks like there's a hole in here where I can substitute a type. So I use underscore as a name for a type parameter. Or if you have a lambda expression in C#, like x arrow, and now sometimes I want to do something here like it's a delegate. Well, if you use anonymous delegates, you can write delegate, you can write here delegate curly open. But if you use lambda expressions, you have to provide the parameters. And for example, when you do event handlers, you have to do the sender and the event args, and often the sender is kind of not used. So I'll write it like this. I just write an underscore for the sender, and then bind only the event args. So that's kind of a little trick that is kind of inspired by the use of Haskell's wildcard patterns. All right. Now you think that functional programmers are don't care about efficiency. But if you look at this definition here, it kind of has to evaluate when it pattern matches, if Haskell pattern matches, it pattern matches like, you know, things from top to bottom, left to right. So for this definition, you have to evaluate both the arguments here in order to return true. Okay? But, you know that if this guy is true, then the result of AND is whatever that second argument was, right? Because if it's true and true, it's true. And if it's true and false, it's false. So a more efficient definition would be to say, well, if the first argument is true, well, then the result is whatever the second argument is. And then you make this one here. If the first argument is false, well, then the answer is always false. Okay, so now you have kind of created a little more efficient example that doesn't really require to evaluate the second argument at all. Now this is interesting because in Haskell I lied to you, right? Because when I said that bool had only 2 values, really in Haskell it has 3 values. And this is not nullable of bool. It's because in Haskell, because it's lazy, every type has also a value called undefined or bottom. So though the values of type bool are, I should write this properly, are true, false, and bottom, which is the non-terminating function that will return a bool. But since it's lazy, you don't know. So it can be, you know, it's not a value that you can pattern match, but it's a proper value of something of type bool. And in this case, you know, if you apply this guy with a second parameter, a non-terminating function, it will just return that non-terminating function, but it will never touch it. And so if you don't then not use the result of the Boolean, it will never happen. So let me give you an example, because I agree this might sound a little bit abstract. So let's define a function f of x equals 13. I like 4, 7, 11. That's my favorite integer. So I define a function f, takes an argument x, ignores it, and just returns 4, 7, 11. Now if I call f of true and bottom, well, since true and anything is anything, so this is f of bottom, but f of any argument is 4, 7, 11. So this is 4, 7, 11. So even though this thing is something that does not terminate, and the way you define it is you would define bottom is a recursive definition that immediately goes. So this is like a function that, like while true, do nothing, right? This thing will properly terminate. Whereas if we go to the previous definition here of AND, this one will, you know, when I try to call it with a non-terminating function, it will go wrong because that doesn't match true or false. So in Haskell you have to be really, really careful with laziness, and especially with pattern matching, because sometimes, you know, well, pattern matching introduces eagerness because it kind of evaluates the arguments in order to match it. And that's kind of, you know, one of the few places in Haskell where you introduce eagerness. Another one is like certain other functions like addition, but conceptually you can view them as doing pattern matching as well. You can imagine that you define addition by a big truth table that just has, you know, all the integers and just it gives you the values for them. So in Haskell you have to be really careful whenever you have a function that introduces strictness, how it kind of deals with this bottom value. And of course in an imperative language or like a normal language like C# or F#, all the arguments are evaluated eagerly. So in this case, you know, before you would even do the pattern matching on F, you would, you know, evaluate both these things, and this would never terminate. So the result of this call would be bottom, kind of right here, right at this call. this thing would never terminate. So that's the difference between lazy evaluation and eager evaluation. However, here you also see the nice thing, the beauty of lazy evaluation is that it supports equational reasoning. I can just, take a expression and take any sub-expression and just, rewrite it, without looking at the context. So in this case, I don't have to check whether this thing is inside F. I can, reduce this thing to bottom. I could also have gone the other way, which would have been more Haskellish. So F of something equals, so I can go this direction, or I could have gone this direction and said, well, F of anything is 4, 7, 11. So no matter, and that is the same here. So it doesn't matter what evaluation order I take, the expression always has the same value. And that is the kind of real power of lazy evaluation, is that you abstract from the evaluation order. It doesn't matter if I evaluate the argument first or if I evaluate the argument later. And that is why Haskell is so popular, or pure functional programming is so popular for concurrency, or for parallelism I should say, is that the compiler or the virtual machine can decide, in what order it evaluates things. Whereas if you're in an imperative language with side effects, you cannot do that, because the evaluation order is dictated on you by the language spec. I cannot, I have to evaluate this thing first, and I have to evaluate each of these first, and then you get very different semantics. So again, this simple example, really, really simple, but it already shows the enormous power of lazy evaluation and the fact that, evaluation order is irrelevant. So the big thing of pure functional programming is that we abstract from the order of evaluation. So we abstract over a lot of things in C#, like memory, right? We don't do garbage collection, but we don't abstract over the order of evaluation. The order of evaluation is explicit. In Haskell, the order of evaluation is implicit. Okay, so that was a brief excursion into lazy evaluation and purity. We will see much more on that in future lectures, especially when we start to talk about monads and side effects. Okay, so here we have the fast definition, and as I said, patterns are matched in order, top to bottom. So if you would write this definition for AND, if you would switch the arguments and the results around, so I would start with I would say, something and something is false, and then the other one is true, and true equals true. Well, this would always return false, because in Haskell the patterns are matched top to bottom, left to right. And that's also different in other languages. Some languages say all the patterns must be exhaustive, and then you can reorder the patterns. But in Haskell that's not the case. You write them top to bottom, left to right, and that kind of allows you to do these wildcards, because maybe now you might have not given all the proper patterns, but that's okay. That's the same as when you're doing dynamic dispatch, that some of your methods might throw an exception. There's nothing wrong with that. I think having partial functions, that's a fact of life. So I'm not a big believer in complete pattern matching where you have to give all the cases, because you want to write partial functions that are not defined on all their arguments. All right, so enough of Booleans. Let's look at some more interesting types. And we've seen our good friend lists a couple of times in previous lectures. And you know, I mentioned this before, but now the time has come to really explain it. If you write a list like this, so this is a list with square brackets, right? This has type a list of int. And you write a list by putting the elements between square brackets, but really this is just syntactic sugar. This is not, you know, it's just like an abbreviation for writing the list using its constructors. So that's like 1 cons, which is an infix operator just like plus, which takes an element and a list and creates a new list. Or maybe, you know, this is like, you know, an element and this is a list and I cons it. So you can stick it together like Lego bricks. So 1 on top of 2, on top of 3, on top of 4, on top of the empty list. Okay, and it's kind of weird that the empty list is written with square brackets, but hey, you know, let's see, do we have the 1, 2, 3? I'm missing a closing paren. So this really means exactly the same. So whenever you write a list with square brackets, it's really an abbreviation for something with the cons operator. And then the reason that we want to do this is because we want to often do pattern matching over lists. So we have seen, you know, in previous lectures functions over lists. So for example, the function head, and let's write its type. It takes a list of A and returns an A. So this is a very interesting function. If you look at head and you look at its type, there's really, you know, not very many choices to do this. You can take the first element, well, in principle you can take any element of the list, right? But that's kind of all you can do. When you look at this type, there's no way that for all types A, when you get a list of A, you can return to me an A. Well, there's one way I can do it by returning you bottom, this non-terminating thing, but all the other ones are, well, I have to pick some value out of this list. Well, and since lists are built using this pattern, really the easiest way to define this function is as follows. If I have to take the head of a list that has a value A on top of another list, well, then I return A. And since we're not using that rest of the list here on the right hand side, you can be cheap and say we're not giving that a name. All right? And this is a perfect function definition, but remember, as I said, these functions can be partial, because what happens when I apply head to the empty list? Well, that's undefined, right? So if I say head, let's write that here, if I do head of the empty list, well, there's no pattern that matches that. So one way to kind of, you know, think about that is that when there's no pattern that matches, it takes arbitrarily long to kind of, you know, come up with a result. So one thing to kind of just imagine, when there's no match, the result will be bottom. So it's like, you know, it's like a non-terminating thing. So an error in Haskell, very often you can just say, when there's an error, you just say that's like a non-terminating function. The interesting thing is, if you look at distributed computing, where you know, things can take a long time, so I'm making a network call that might have a large latency, it's also kind of weird to talk about errors, because how do I know that this network call has failed, right? If I don't hear back in 5 minutes, 10 minutes, an hour, maybe I never get back the result. So really, you know, in those cases, talking about errors, distinguishing between errors and non-termination doesn't make a whole lot of sense. And in Haskell it's kind of the same. in most cases you can assume that an error is kind of the same as non-termination. It's not always the case, but it's kind of, as a conceptual model, that is, I think, pretty useful. Again, because if there's an error and I'm never using this, let me go back to that example I gave before. If we have f of x equals 4, 7, 11, if I now call f of head of the empty list, well, since this function here doesn't need to evaluate its argument, it will return 4, 7, 11 immediately. So that's here. I can return 4, 7, 11. Or I can say, well, the head of the empty list, well, it's something that doesn't terminate, right? So I go this direction. Here I go that direction. And then I can say, well, f of anything is 4, 7, 11. So this is, again, 4, 7, 11. So it's kind of okay to just leave things that are errors just there and treat them as not terminating until you really touch them. But in this case, I can continue the evaluation without ever having to evaluate the head of the empty list. So again, it's all equational reasoning down here. So errors, think of them just as non-terminating computations. And then the other function, of course, if you have head, you want to write the function tail. Let's write down its type. So tail takes a list and returns another list. Well, if you look at this function again, if you look at this type, it says, given an arbitrary list of elements of type A, return to me another list of type A. I can only think of maybe 4 functions that satisfy that type. One is the identity function, right, that just returns that list. But that's kind of cheating, right? Because that has really type for all A arrow A. So that's not a good solution to this type, because that has a more generic type, a more general type. Then the other thing I can do is I can return the empty list, right? Given any list, I can return the empty list. That's kind of cheating too, right? Because I'm not really using that argument list here. So in that case, maybe I'm going to take another pen here, and I'm going to wipe this out. So our first thing we said we were doing tail. We're going to invent tail by looking at the type. Okay? So the first attempt was to say, tail takes a list and returns a list, so tail of some list equals that same list. Right? That's one thing that satisfies this type. But as I said, really, that type, when I write tail like this, has type tail, has type A, arrow A, because it doesn't really require that thing to be a list. So we can, that's why it's in red, this is not a good definition. So the next one we said, if we define tail of A's to be the empty list, right? Now in this case again, we're not assuming that this guy is a list. So really the type of this tail is, well, B, arrow, well, what can this be? List of what? Well, let's say, it's a list of A or something, right? Because it can be any list there. So this is also not the right type, right? It takes any argument and returns a list, but the argument and the result are not even related. So that's also a wrong one. And then the other thing we can do is we can say tail, and we can return bottom, right? The undefined element. So we can say, given A's, I can return bottom. Well, really, what this type is tail takes a value of type A and it returns some value of type B, where this is unrelated. So that's kind of also not it doesn't fit this definition. So by just inspecting the type, really the only reasonable choice that I can make for tail is tail has the following type. If I have a list of A's followed by A's, I return the tail. And this might look like a trivial reasoning, but one of the real deep values of a pure functional programming language like Haskell is that you can really trust the types. When you look at the type of a function, that really tells you a lot about that function. So when you know the type, you know an awful lot about that function. Just like here, just by looking at the type, I could rule out a lot of these kind of cheaty definitions for tail. And I was kind of, led more or less straightforwardly to this definition. If you kind of, like to get more deeper into functional programming, Phil Wattler has written a great paper. Phil Wattler. I also recommend the Channel 9 interview that I did with him a while back. But Phil Wattler has written a paper. Everyone that's interested in functional programming should read that. It's called Theorems for Free. And I think it even has the exclamation mark in the title. And what this is about is that it says when you look at the kind of, the polymorphic type of a function, from that type you get a theorem that that function satisfies. And again, that really relies on the fact that the type says everything, that the type doesn't hide anything from you. That, even if you say this takes a list of A to a list of A, that it doesn't do anything under the covers, that it doesn't do kind of side effects under the covers, reflection or whatever. So the fact that you have a pure language allows you to kind of, infer a theorem for each type. So I can really recommend everybody read that paper. It's one of the best papers in the functional programming literature, and it's a paper that I kind of every year around Christmas time I print it out again and I read it again, and it's just a joy to read. All right, as I said, patterns can be non-exhaustive, so you can define partial functions. And in this case, when you define the head of the empty list, or when you try to execute the head of the empty list, you get an error, or as I said, is undefined. The other reason, the other kind of little nitpicky thing, and I'll leave this great paper here for a little bit. You have to kind of put parens around the pattern. So if you write head of x colon axis equals, let's see what he has here, x. This gives you a syntax error because application binds stronger than cons. So you have to kind of write it like this, because otherwise it kind of, I think if you don't put that, it reads like this. Application binds stronger, And while you can define a definition like this, this guy on the left-hand side is not a pattern. So this will be, it's an error. So you have to put the parens there. And again, this goes back way to our first lecture where we talked about the fact that application is so important in Haskell, and that's why it binds strongest. Okay, so a little bit here. So then there's something that's kind of quite controversial in the Haskell community, and this is called n plus k patterns. And some people are really kind of viciously objecting against them. I think they're pretty neat. So they allow you to write patterns over integers, but only of a certain kind, where you can write something, a variable plus a constant. So that's why it's called n plus k. So I can write, what is the predecessor of a number? Well, the predecessor of n plus 1 equals n. Okay, and this is something that you see in a lot of mathematical textbooks, But and if you remember the various talks that the interviews that Brian Beckman and I did, in physics and in math, you can be imprecise. So you can write kind of definitions like this and kind of wave your hands and it's clear what they mean. However, if you define a programming language, the semantics of what these patterns are exactly is not always clear or not always what you expect. And that is the reason that people don't like them. But I think it's pretty neat, for example, and I shouldn't really use factorial or Fibonacci, because that's the kind of cliche example that we always use in functional programming. But still, it looks nice. So if I define, the factorial of, what is it, 0 equals 1, and the factorial of n plus 1 equals n times, n plus 1 times factorial of n, something like this. So when you write a function by induction over numbers, you kind of don't have to write n minus 1 on this other side, you write n plus 1 on that side. So that's just, and again, you could just write n minus 1 on the other side. It doesn't really matter. This one reads a little bit nicer. And again, just like cons, you can have n plus 1 patterns that are partial, and also you have to put parens around them again, because application, like when you write pred n plus k, the pred of n binds stronger than the addition. Okay, so much for like function definitions that have a name. Now, lambda expressions are the big craze, right? Every language seems to have them. Python, Ruby, C#, even VB has lambda expressions. And lambda expressions, as we saw in the first lecture, come from Church, from the lambda calculus that Alonzo Church defined. And in Haskell, lambda expressions are written, using a lambda notation. And in the slides, it's written with a more beautiful lambda and like a beautiful arrow like this. Lambda x, x plus x. And when you type that in the keyboard, you type, x. But you see, it's kind of close enough. It's just, this is your keyboard, and if you would use Unicode or something, that would always be more awkward to write down. Okay, and what is this? Well, this is an expression of the following type. It's an expression that takes an int and returns another int, right? And again, you see that as we discussed in lecture 3, the structure of the type and the structure of the expression is very, very kind of, close. It mirrors the structure of the expression, mirrors the structure of the type, or the other way around. So just like in C#, you would write this guy as x arrow x plus x. And I think in VB, you write function x plus x. So each of these are just the same thing. It's like you want to create a function that you want to pass around, but you don't want to give a declaration. You just want to create a function just like you want to create an integer, 5 plus 3. And if functions are first class, of course, they must be just normal values. And that's what lambda expressions do. This is like a constructor for a function. Okay. And as I said before, lambda comes from the Greek letter lambda, that comes from the lambda calculus of Church. As the slide says, sometimes, and probably Brian would write it like that, you write, you write it with this kind of arrow, you don't write a lambda in front. There's many ways for people to write these lambda expressions. Okay. This is what we already discussed. Why do you want to use lambda expressions? Well, it's when you're kind of lazy, right? it's like when you're lazy, you don't want to give a name, but also it kind of reflects the type. So if I write x, add of x and y equals x plus y, that is the same as saying add of x equals lambda y, x plus y, which is the same as defining add to be the function that takes a function and returns x plus y. Okay, so these are all the same. The following example shows when these lambda expressions are useful. And again, this is a matter of style. When do you write your function definitions with all the arguments to the left? When do you write them as lambda expressions? So in this case, when you define the constant function, you know, it's a function that takes a value and then returns a function that throws away its argument. So that's much better expressed in the second declaration that you see on the slide there. The const of x is a function that doesn't look at the argument and returns the original function. Okay, and here's another example where you often use lambda expressions, and that is kind of the same reason why you do that in C# actually. If you want to write, if you have a function that you only use once, like in the previous example, where I have odds that maps some function f over a list, you know, list of integers from 0 to n minus 1, I'm only using that f only once. So why would I spend my brain cycles to invent a name like f? I can just inline that function definition as a lambda right there instead of f. All right, so I'm going to close down now with something that I really miss in C# and VB, and that's the notion of a section. So in Haskell, whenever you write a binary operator like 1 plus 2, you can easily use that operator as a function. So when you write 1 plus 2, you write this thing as an infix operator. If I put parens around it, plus, now suddenly it's become a function that I can apply to 1 plus 2. So this is the same. If I would do this in C#, I would have to write x arrow, y arrow, x plus y, you know, 1, 2. So I would be forced to write a lambda expression that kind of gives names to the parameters here in order to use that thing as a function. And so often you want to pass around a binary operator as a function, like for example in LINQ, when you're doing an aggregate, I want to sum the elements of a list. Well, I need to pass addition into that, and then I have to kind of write it like this. And here you see this is all noise. This is all noise. The only thing that's important here is that I want to pass in the addition function. You can even go further. What if I want to have a function that adds 1 to its argument? Well, I just write 1 plus, which is the same as lambda x 1 plus x. And again, if you look at this expression here, this is all noise. Right? So it's really, the important thing is that I want to add 1 to something. This is not noise. I should keep that blue. Okay, and then of course you can do it the other way around too. I can say plus 2, and this is the function that adds to the other side. So as the slide says here, you can take any binary operator and section it by partially applying that. And that is something that's a little syntactic trick that, you know, I wish other languages would also take over. Just like they have taken over lambda expressions, they should also kind of take sections. And here you see a whole list of sections, like, you know, increment function, you know, taking the opposite, doubling, etc. Okay, so we're now at the end of this lecture. A couple of exercises. As I said, one of the exercises was to define AND in terms of double dispatch. Here is another one that is called save tail. But except when you have the empty list, it returns the empty list. And the question is to define them in a couple of ways. And again, there's a library function that checks whether a list is empty. You can easily define that yourself using pattern matching as well. Then the other questions are just, play a little bit around with different ways of defining the end function using pattern matching, using conditionals, just like kind of what I did on the board previously, to get a feel of how that pattern matching works. So that was all for today. This was our first lecture where we really started to do programming. Next week we'll start doing some more complicated programs. We'll talk about recursion, about lists. So keep watching, keep doing your homework, and I'll see you next time around. Thank you very much.